previously we looked at quadratic approximations, and what the idea was is we wanted to extend linear approximations. So linear approximations, if I start back here, had this interesting property that the linear approximation of at a point x equals a is equal to the function at x equals a, and the derivative of the linear approximation at x equals a, it matches the function at x equals a. But these linear approximations, they are limited, right? We're trying to approximate something curvy with a line. So if we're going to approximate something curvy, why don't we use something that's curvy? And that's where we came up with this idea of a quadratic approximation. So I wrote out a general quadratic function. And then the idea that we wanted to have here is that the quadratic function would match our function f of x at the point x equals a, that the derivative would match at x equals a, and then the second derivative would match at x equals a. So last time we worked through that, we looked through the conditions that would make this quadratic function match, and its derivatives match at x equals a. And from that, we were able to solve for these coefficients. So we were able to show that the first coefficient is f of a, the second one's f prime of a, which if you look to the right here, that meant that the linear approximation, it was in fact the first two terms of our quadratic approximation. And then the last coefficient was actually 1/2 f double prime of a, and that's sitting inside of that quadratic term, x minus a squared. These were easy to find, f of a, f prime of a, f double prime of a, for the function e to the x, because the derivative of e to the x is also e to the x, and so is every other derivative. And so we were able to easily find the coefficients, and then from there we were able to find a quadratic approximation. Okay, so the quadratic approximation there for e to the x is 1 plus x plus 1/2 x squared. Now you can plot this in Desmos. Okay, and so let me just plop this down for a second. So on the screen, hopefully you see the red curve is e to the x. 1 plus x is the blue line, which is a decent approximation, kind of near x equals 0. But a better approximation was the quadratic approximation, because it really follows that curviness. Okay, that curviness to the function you can see with that quadratic approximation. Now what I would like to do is extend that approximation not just to quadratics, but cubics, quartics, quintics. I want to do higher order approximations of functions like e to the x. Okay, so this is what we're going to head toward. One thing before that I want to mention, though, is we can use these approximations to estimate things like e to the 0.1 power. Notice that e to the 0.1, if you put it in a calculator, is 1.1051709. The linear approximation is 1 plus 0.1 or 1.1, and that's good to 1 decimal place. It's accurate to 1 decimal place. But the quadratic approximation, q of 0.1, is 1.105, and that is accurate to 3 decimal places. And so what we're hoping is that if I did a cubic approximation, that would be, say, accurate to even more decimal places. And then this gives us a way that we can approximate functions like e to the x. Okay, so our new method is going to be called Taylor polynomials. Taylor polynomials are polynomials of the form a0 plus a1 times x minus a plus a2 times x minus a squared, and then adding more terms with x minus a to the n power. So this is an nth order Taylor polynomial. Okay, I'm going to go back real quick, just so that people can see this part of the example, because I went by it really quick. Okay, but I'll just talk about this idea of Taylor polynomials while we've got this example up. So the idea is that we're going to have this polynomial, and then what we want to do is we want to match derivatives of the Taylor polynomial with my function at some point x equals a. So we want the polynomial at a to match f of a. We want the derivative at x equals a to match f prime of a, the second derivative to match f double prime of a, just like we did with the linear and quadratic approximations. But we want that to continue all the way to the nth power. Okay, so now I'm going to look at these Taylor polynomials. And so when I look at this, I want f of a to match my polynomial at a. And so I'm going to plug in what a is to that polynomial. And when I do that, I notice that this, they all become 0. Okay, all of those things are going to become 0. So because those are all going to become 0, I'm left with just the a0 term when I plug in a. Now the derivative of my polynomial, I'm actually going to take the derivative kind of right here. So I'm going to call this Pn prime, and I'm going to take the derivative. The derivative of a0 is 0, okay? And then the derivative of a1 times x minus a is just a1, so that's going to go away. And then the derivative of a2 times x minus a squared is going to be 2a2 x minus a to the first. Then we're going to get 3a3 x minus a squared. And then finally down to n x minus a to the n minus 1. And then what we're going to do is we're going to plug in a. And when we do that, okay, we're going to be left with just the a1, okay, because I've canceled out the x minus a there. And then 2a2 a minus a, because here I'm going to have x equals a, so that's going to go away. And then this one will have an a minus a in it, and that will go away. And this one will have an a minus a in it, and that will go away. So all that's left is just a1. So then after that, I'm going to take a second derivative. So I'm just going to put another prime there. Okay, now the second derivative of a1 times x minus a is going to completely go away. Okay, and then 2a2 times x minus a, well, the derivative of x minus a is going to be 1, so that part goes away. And then 3a3 x minus a squared, I'm going to take a derivative that's going to be 3 times 2 a3 x minus a to the first power. So I'm going to take another derivative there. Eventually, I'm going to be down to, I'll just put it there, n times n minus 1 a sub n to the n minus 2 power. And so my f double prime of a here is actually going to be just 2a2, because when I plug in a to other terms like here or here, the rest of that stuff goes to 0. So that actually tells me that a2 has to be, like we said before, 1/2 f double prime of a. We've so far realized that a1 was f prime of a, and a0 was f of a. Okay, so now I'm going to take another derivative. So if I take another derivative, the third derivative here, then the derivative of the 2a2 goes away. So now this is gone, okay? Take the derivative of this a3 term, and I get 3 times 2 a3, and then the derivative x minus a is just 1, so that goes away. And as I continue this progress, I'm going to get n times n minus 1. The n minus 2 comes down, and then I'm left with n minus 3 power there. Now, if I start plugging in a, my first term looks like 3 times 2 a3, But every other term after it has an a minus a in it when I plug in a for x. And so I'm going to get 0 there. And so I'm just left with 3 times 2, a3. So that tells me that a3 is 1 over 3 times 2 f triple prime of a, which sometimes we notate because we don't like writing so many primes. So we do f with a 3 in parentheses of a. That's the third derivative. Now, hopefully, I didn't put it in here, but let's go ahead and put the fourth derivative in there. And hopefully what you'll see is that the fourth derivative of this function at a ends up being 4 times 3 times 2, a4. So that a4 is actually going to be 1 over 4 times 3 times 2 times the fourth derivative at a. So if you're seeing a pattern here, it looks like the nth derivative, because I have to keep taking more derivatives, right? N times n minus 1 times n minus 2. If I take another derivative, that would get multiplied by n minus 3, and I'd have n minus x minus a to the n minus fourth power. So what you're seeing is that the nth derivative ends up being n factorial a sub n, okay? And that tells me that a sub n in this case is 1 over n factorial nth derivative of f at x equals a. So that's the general formula for one of these Taylor polynomial coefficients. So now I can write out what the polynomial is. It's going to be a0 plus a1 times x minus a plus a, oh, why did I write that? It's going to be f of a plus f prime of a times x minus a plus 1/2 f double prime of a times x minus a squared plus 1 over 3 factorial third derivative at a times x minus a cubed. And then finally, we have 1 over n factorial when we get to the n times the nth derivative at a times x minus, running out of room here. Let's see if I can scoot it over just a little bit. X minus a to the nth power. Okay, another way we can write that is we could write that as being the sum from n equals 0. Oh, I want to use a k there. K equals 0 to n of the nth power, or sorry, the nth derivative of f at a divided by n factorial times x minus a to the nth power, kth power. Whew. Try that again. Kth power at a divided by k factorial x minus a to the kth power. And that's called a Taylor polynomial for f at x equals a. So this is a way to approximate the function f of x near x equals a using a polynomial of order n. Note that these factorials came in. Remember, we were doing some series stuff with factorials, and I said, oh, don't worry, we're actually going to need these factorials later. I'm not just, throwing in math symbols for fun. Like, this is actually going to be important later. And so hopefully you'll start to see the connection that we're going to make in the near future with series. So that's my Taylor polynomial formula. So I'm going to leave that up right there. And then what I want to do is I'm going to find the 8th degree Taylor polynomial for e to the x. And so what's important here to notice is that the nth derivative of e to the x is always e to the x. And so the nth derivative at x equals 0 is always e to the 0, which is 1. And so my Taylor polynomial for e to the x is going to say that e to the x is approximately the 8th degree Taylor polynomial. And that is equal to, the first term is f of a, so e to the 0 is 1, plus f prime of a is also 1, so that becomes times x minus a, but a in this case is 0, so this is a right there. I'm going to do a 1/2 times f double prime of a, which is 1 times x squared. Okay, the next term is a 1/3 factorial times 1, because that's the third derivative, x cubed. You'll start to see a pattern, 1/4 factorial, x to the 4th, plus 1/5 factorial, x to the 5th, plus 1/6 factorial, x to the 6th. I'm going to keep going, plus 1/7 factorial, x to the 7th, plus 1/8 factorial, x to the 8th. And using that polynomial, we can get a good approximation of e to the x, okay? Near x equals 0. And so I'm in a moment going to show you what that looks like when we graph it in Desmos. I just want to make sure that everyone gets a chance to write some of these things down. Of course, I'm posting these notes as well if you need them. Okay, so in Desmos, this is where we were. I came up with a function t of x. T of x is the sum from k equals 0 to n of x to the k over k factorial. That's because the coefficient is supposed to be the nth derivative over k factorial, but in this case, the nth derivative is 1. So we get x to the k over k factorial. And then right now it's summing to 2, so it's got the quadratic, but now the purple one is going to be the cubic. So now you can see the cubic is a little bit better approximation. It's between the green quadratic approximation and then the red curve there. Okay, now here's the quartic approximation, which if you look at it is really, really close to the red curve between -1.5 and 1.5, right? It's really, really close there. You can hardly see the difference. Now I can do a quintic polynomial and it's even closer. I can do 6, 7, 8. 8 is going to be the polynomial that we are looking at. Notice that you can hardly tell the difference between the polynomial there and e to the x. You have to zoom out to see where they finally are different. So I can zoom out here and we can see that where they're finally different. Right around -4, we see a difference. And I can even start to see a tinge of red there at 4. So it's between -4 and 4 that you start to see a difference there. So as I increase, right, you can see that it extends my approximation further out. If I use 20 terms in my Taylor polynomial, in this window between -6 and 6, they look pretty identical. We can use that to even do things like approximating 0.1. So we can approximate 0.1 that way. Let's go back down to our 8th order polynomial for a second. Notice that, wow, the 8th order polynomial for e to the 0.1 agrees in all decimal places given by Desmos. Okay, so that's 11 decimal places or something, right, that agree in that sense. This gives us a wonderful way to compute e, for example. If you want to compute e, that's e to the first power. E is just going to be 1 plus 1/2 factorial, or sorry, 1 plus 1 plus 1/2 plus 1/3 factorial plus 1/4 factorial plus 1/5 factorial. And you just keep going And you can see you're approximating E with 8 terms. It looks like it matches 1, 2, 3, 4. 4 decimal places match. If I go out to 20 terms, I can get the entirety of Desmos is approximation to match for E. So that gives you kind of a use for Taylor polynomials, okay? Like, see, you can use it to approximate e to the x near x equals 0. Okay, I'm going to move on. I'm going to show you how you would do this problem for square root of x. So I'm going to calculate square root of x at x equals 4, because I want to do a Taylor polynomial that's centered at x equals 4. So square root of 4 in this case is going to be 2. The derivative is going to be 1/2 x to the minus 1/2. And so the derivative at 4 is going to be 1 over 1/2, and then 4 to the minus 1/2 is also 1/2, so I'm going to get 1/4. F double prime of x is going to be, let's see, minus 1/4 x to the minus 3/2. So F double prime of 4 is actually going to be, let's see, 4 to the minus 3/2. That's going to be 1/8. So I'm going to get minus 1 over 32. The third derivative of x is going to be a positive 3/8 x to the minus 5/2. So the third derivative at 4 is going to be, let's see, 4 to the minus 5/2 is 2 to the minus 5. So that's going to be 1/32. So 1/32 times 8 is 64. It's 256, I think. Please double check me if I'm getting any of these wrong. I believe that's going to be 3 over 256. And then the fourth derivative of this is going to be negative 15 over 16 x to the minus 7/2. So that's going to be the fourth derivative at 4 is going to be a negative 15 over 16 times 2 to the 7th. So that's going to be 2 to the 11th power. Can somebody tell me what 2 to the 11th power is?
(2048).
Okay, that sounds right from last class. 2048. Perfect. Okay, so we can approximate square root of x by a Taylor polynomial of degree 4. And it looks like this. It's going to be 2 plus 1/4 times x minus 4, because it's times x minus a, minus 1 over 32 divided by 2 factorial, x minus 4 squared, plus 3 over 256 divided by 3 factorial times x minus 4 cubed. And I certainly did not give myself enough room here. This is going to be minus 15 over 2048 divided by 4 factorial, x minus 4 to the 4th power. Okay, so that is going to be my approximation of square root of x. And so if I want to find square roots of numbers that are near x equals 4, like this is how you do that. Okay, so So this is how you would find those approximations. Yeah, I mean, and you can simplify this obviously, but I don't have the time to do that right now. Okay, so I want to actually show you that approximation. Here is square root of x, that is the red curve, and then the fourth order Taylor polynomial is actually in blue. And notice it seems to be a really good approximation between about 1 and 7. See if I can get it to give me 1 and 7. There we go. So between 1 and 7, I feel like I have a really good approximation of square root of x. So if you want to find things like, let's say you wanted to find the square root of 4.1, obviously, a calculator can do it now. It's 2.0248. But if you didn't have a calculator, you would have to do the polynomial at 4.1, and notice that it's good to about 6 decimal places, right? So that Taylor polynomial at 4.1 is good to about 6 decimal places.